So 7.5 is about proportions and similar triangles. So our objective here is to use triangle proportionality theorem and its converse. So your first definition's on top, the divided proportionality, when two ratios of two segments with corresponding lengths are equal. So this is where we did before, we compared the triangle side to see if the ratios were the same, to see if we had similar triangles. We're now going to apply that to segments. If they have the same ratio, we're going to be able to say that they're proportional. We're going to look at our comparison of lengths of AB to BC. So what is our length of AB? 2. What's our length of BC?
3.
So since it was written with the colon, I'm going to continue to do this. So 2 to 3. And then we're going to look at DE to EF. What's the distance of DE?
4.
And what is it of EF? If we reduce that ratio, what would it go to? 2 or 3, because 2 goes out of both of them. Okay, so are those ratios the same? So we would be able to say, yes, they're proportional with a ratio of 2 to 3. Those little dots look terrible, so 2 to 3. So here we see if a parallel line to one side of the triangle intersects two sides, then it divides the two sides proportionally. So with this, you see if it's parallel, then you have RT, which is the top part of the triangle, and then it's over just the bottom part. So yesterday we added both halves of the triangles to create that ratio. Now we're only using what you guys wanted to do, that quicker method, so just using the bottom part. And then you have RU over just the bottom part again. So we're splitting those sides. Okay, so for this one, the side splitter theorem, you can now see that this one is the smaller top part over the whole, smaller top part over the whole, and then just the two sides over each other for the bottom. Okay, and so then we can also see that we could break it down to AB over CD just like we did on the other one. So this is just putting it all together. Okay, so here we're going to use that theorem again. And remember, we can do the small part over the little, like the small part of the triangle, so the 22, over the portion that makes the big side. So in this case, that would be the X. So it's not the whole anymore, it's just the extension. And then we compare it over here to the 20 over the extension again, 10. And then we're back to just cross multiplying. So if you guys remember, dividing by 10 would cancel out these zeros. And then we can do 22 times 1, which is 22. 2 times x, which is 2x. We got to get x by itself, so we divide by 2. X equals 11. Yep. Here again, we're going to do that same theorem. We're going to use the fact that it's the small part over the addition to make it the big part, so 10 over 14. And for the bigger triangle, or for the other half of the triangle, the other side, it's y over. What's the length of the bottom part here? So we don't officially know this, right?
No.
So if we know the whole thing's 36, and we know that y is the top part, how much is left down here? We don't know that for sure because we don't know if it's directly split congruently. 36 minus y. So the way to accommodate for it, so you want to be careful, is it's 36 minus whatever you used above. So 36 minus y. So that's going to be our denominator. And then we cross multiply again. 10 times 36 minus y equals 14 times y. I'll do the first part. 360 minus 10y equals 14y. What do I do next?
Add 2.
Yep, add 10y. I have 360 equals 24y. We got to get y by itself.
Divide 24.
Y by 24. Y equals? Can you say it a little louder, hon? 15? Thank you. That is a 5. Here we're determining whether it's parallel, and so we had to see if those proportions are going to be the same. So we're going to write these out. Let me go back. So we're here. So we're going to write that 56 over 48. So the top part over the portion we add to make the big length. And then on this side, we have the top part being 21. And then the big part that's adding it to make it is going to be that 16. And we have to see if these two fractions are going to be equal. So what goes into both 56 and 48? 8. How many times does 8 go into 56? How many times does it go into 48? What'd you say, hon? 6. So we have 7 over 6. What goes into both 21 and 16? Nothing. So does 7 over 6 equal 21 over 16?
No.
Nope, not parallel. Because 7 over 6 does not equal 21 over 16. So when we're looking at this, you see a bunch of congruent marks, but we only have one real number given here. So we're going to have to use this theorem that we already put up at the top to look at it. So we know that the length of AX is the length AX. We don't know what it is, but I can use it just to talk about it as AX. If you know these two are congruent, what's the length of AB?
X.
Not exactly. So if you know they're congruent, we have one AX up here. How much has to be down here? Another AX. So how many AXs do we have?
2AX.
2AX. And we can apply that same idea to the other side. You see you have AY up here. You see that they're going to be congruent, top and bottom. So the whole length is going to be how many AY? 2AY. And then the last part, based on that theorem, is just talking about the bases, x over 16. So you have the same thing in the numerator and the denominator. What can we do with that?
Add them together.
So we can cancel them out. So it's like having a 2 and a 2. So they just go away. So we have an AY over AY here. So you're left with 1/2 equals 1/2 equals x over 16. You might be able to look at that and see what you'd be able to put in the numerator to reduce that down to 1/2. If not, we can do some cross multiplication. If you're doing that, you have 16 equals 2x. Divide by 2, x equals 8. Nice job.